The displacement of particle executing simple harmonic motion is given by y is equal to a sine omega t. The work done by an external force against the restoring force in displacing the particle from its mean position to displacement is given by w is equal to half ky square. When the body is subjected to external periodic force, it oscillates with the external periodic force. Such oscillations are called as forced oscillations. Hello everyone, welcome to session 2 of chapter 14 Oscillations. This is Swati from Department of Physics, Vidhyaashram Pre-University College, the Temple of Excellence, Mysuru. Dear children, according to simple harmonic motion, we all know that the acceleration is directly proportional to displacement and it is always directed towards the mean position. So here there is a concept of direction. And how to prove that the acceleration is directly proportional to displacement and it always directs towards the displacement? For that, we have a proof. We can show that in simple harmonic motion, the acceleration is directly proportional to displacement at a given instant. For that, we have a derivation as follows. The displacement of particle executing simple harmonic motion is given by y is equal to a sine omega t. Generally, we call this as displacement equation. So, assuming here the initial phase is 0. So, the instantaneous velocity, which means the velocity of an object which is undergoing oscillation at any instant of time, is given by v is equal to dy by dt, that is rate of change of displacement. So, if we differentiate a sine omega t, we get a omega cos omega t that I have already shown in the previous class. Like you have to derive this in with the help of a chain rule, which means d by dt of sine omega t is cos omega t, but omega is the function here. So, omega cos omega t we get. So, now if you differentiate this again to get acceleration, you will get minus omega sine omega t. So, the instantaneous acceleration can be calculated by differentiating the velocity term, that is the rate of change of velocity gives us acceleration. So, it is d by dt of a omega cos omega t, where a omega cos omega t is nothing but the velocity term, and a omega you can take outside and differentiating cos omega t, you will get minus omega sin omega t. So, from this we can write a is equal to minus omega and another omega we have here. So, multiplying these two we will get minus omega square a sin omega t. But what is a sin omega t? A sin omega t is nothing but y, that is displacement, and this can be replaced by a letter y. So, it is a is equal to minus omega square y. Here the negative sign indicates that the acceleration is always directed towards the mean position or opposite to the direction of displacement. So, from this we can conclude that acceleration is directly proportional to displacement and it is always directed towards mean position in simple harmonic motion. So, now let us derive what is the total energy of a particle executing simple harmonic motion. If a particle is undergoing simple harmonic motion, it will reach to extreme end when it gets displaced from the mean position, which means the kinetic energy and potential energy may vary, but the sum of these two energies remains constant. So, now let us write the expression for potential energy, for kinetic energy, and let us take the sum of these two to find the total energy of particle executing simple harmonic motion. So, a potential energy is nothing but the energy of a particle due to its position. So, according to the force law in simple harmonic motion, the restoring force F is equal to minus ky. We have derived this. F is equal to minus ky from force law. So, the work done by an external force against the restoring force in displacing the particle from its mean position to displacement is given by W is equal to half ky square. Work done is stored in the form of potential energy. To calculate potential energy here, we need to calculate the work done. So, a small work done is nothing but the potential energy, which means potential energy is stored in the form of work done. So, now we have W is equal to half ky square and here U is equal to W and hence we can write U is equal to half ky square. But what is K? K is equal to m omega square. So, now substituting the same here, we will get U is equal to half m omega square y square. This is the expression for potential energy. Similarly, we can write the expression for kinetic energy. The energy due to the motion of a particle which is undergoing simple harmonic motion is kinetic energy, and it is given by the relation half mv square. But what is V? V is omega root of a square minus y square, we have derived in the previous class. Now substituting the same in the above equation, we will get k is equal to half m. Squaring this, we will get omega square root, and the square will get cancelled, and we remain with a square minus y square. So this is the expression for kinetic energy. Now we need the expression for total energy of a particle executing SHM, which can be calculated by taking the sum of potential energy and kinetic energy, and the potential energy expression is half m omega square y square plus kinetic energy expression is half m omega square a square minus y square. Now we can just write this as half m omega square y square plus multiplying this with the first term, we will get half m omega square a square minus, plus into minus is minus, again multiplying these terms with the other term y square, we will get half m omega square y square. Cancelling these two, that is plus half m omega square y square plus half m omega square y square and minus m half omega square y square will get cancelled, and we remain with half m omega square a square is the expression for total energy of particle which is undergoing simple harmonic motion. So from this we can say that the total mechanical energy of a particle undergoing simple harmonic motion is conserved, which means the variation of potential energy and kinetic energy and total energy with time and displacement can be analyzed with this picture. So you can observe here, this is the total energy of the particle executing simple harmonic motion, and this blue curve is the potential energy curve and this is the kinetic energy curve. So potential energy means energy due to its position. So from this we can say that the kinetic energy is maximum at mean point, and at extreme points potential energy is maximum. Though at various points the kinetic energy and potential energies vary, but sum of these two energies will remain constant, and hence we can say that the total mechanical energy is conserved. So next we'll move on to another important concept, that is oscillations of a loaded spring. So when you try to push or pull the spring which is loaded with some weights, it will undergo oscillation. So from this concept we can derive the expression for time period of frequency of oscillations of a loaded spring. For that we need to understand few important terms. We'll start with restoring force. So what do you mean by restoring force? It is defined as the force which brings the system back to its original position on the removal of external force. So restoring force, it defines itself that it is the force that helps the object to come back to its mean position, or we can say that the force which brings the system back to its original position is called as restoring force. And next we have force constant. It is defined as the restoring force per unit displacement. Force per unit displacement gives us a force constant. So the next one is force law. So what is the statement of force law? It states that the force acting on a particle executing simple harmonic motion is directly proportional to displacement, and it is always directed towards the mean position. It is nothing but the simple harmonic motion concept. So it says that F is directly proportional to Y, which means the force is directly proportional to displacement, or proportionality can be equated by introducing a constant, that is F is equal to minus ky, where k is the force constant and y is the displacement of particle from mean position. So having these concepts in mind, let us now derive the expression for time period of oscillation of a mass attached to a spring. So for this we have considered a spring here which is attached with a mass. Suppose if we push this and release, it will undergo to and fro motion, which means it undergoes oscillation. So consider a block of mass m attached to one end of a light spring having a force constant k. The other end of the spring is fixed to a rigid support. You can observe here, so it's a light spring. So this mass is attached at one end, the other end of the spring is connected to a rigid support. When the block is pulled on one side, and released, it executes simple harmonic motion about its mean position. So if it is pushed and released, it will undergo oscillation, it will execute oscillation, it will undergo a simple harmonic motion. Here the restoring force acting on the block when it is displaced through a distance of x is given by F is equal to minus Ks according to our force law. So from Newton's second law, again we have force is equal to mass into acceleration. Now these two are force only, so we can just equate these two expressions by comparing. So we can write it as minus Kx is equal to m into A. So now from this equation I can write A is equal to minus Kx divided by m. So that is what we have got here. A is equal to minus K by m into x is our third equation. We also have an equation for acceleration, that is minus omega square into x. Now compare these two equations. So we have in the place of omega square K divided by m and x as it is in both the equation. So it is omega square is equal to K by m, and omega will be equal to square root of K divided by m. But what is omega? In terms of t, time period or frequency, we can represent omega. So in terms of frequency it is 2 pi f, and in terms of time period, if you want to represent it as 2 pi divided by capital T. So 2 pi divided by T is equal to root of K divided by m. Then the time period can be written as T is equal to 2 pi into root of m by K is the expression for the time period of a mass attached to a spring. So now from this we can also write an expression for angular speed, that is omega is equal to root of m by K. But what is m? M is the mass of a particle executing simple harmonic motion in a medium, and K be the force constant, omega be the angular velocity of the particle. So that is one of the important derivations, and which is very important question according to exam point of view. Next we have time period of oscillation of a simple pendulum. So for this let us consider a simple pendulum. So one end of this pendulum is attached to a bob of certain mass, and the other end is attached to a rigid spot. Let m be the mass of the bob and L be the length of the pendulum. So in the mean position, the string is vertical. When the bob is pulled to an extreme position, it executes simple harmonic motion along the arc. So the arc, let write it as x. Now this is reached to an extreme position which makes an angle theta here. So theta be the angular displacement and x be the linear displacement of the bob at some time t. Next, there are two forces that acts on this bob, and here this bob has the weight mg, and after it gets displaced also here it is mg, and the other force here acting is the tensional force in the string. So one is the weight of the bob, that is vertically downwards, and tension T along the string away from the bob. You can observe here this is the tensional force acting away and weight mg towards down. So next, the weight mg can be resolved into two components, that is mg cos theta, and this mg cos theta is, if this is t, it is just opposite to t. So here I have mg cos theta, and next it is resolved into another component as mg sin theta, because the bob after it gets displaced it will come back to its mean position. So this component restore the bob to its mean position. So thus the restoring force is F is equal to minus mg sin theta. Why minus? Because the direction is opposite to its displacement, where theta is very small. Since the angular displacement is very small, we can consider the sin theta value as theta only, and hence this expression becomes F is equal to minus mg into theta. Now the linear displacement x can be written as L into theta. How? From our concept, angle is equal to arc divided by length. Here, according to our consideration, this is our arc length, that is x, and L is the length of the pendulum. So from this, x can be written as, or theta is equal to x divided by L. From this, x will be equal to L into theta. But here we have F is equal to minus mg theta, and theta value will be now x divided by L. So substituting that, we get F is equal to minus mg x divided by L. But we also have an equation according to Newton's second law of motion. It is F is equal to m into a, where a is the acceleration. Now both are F only at LHS, so we can equate the right hand side terms. So we get mg is equal to minus mg x divided by L. Here this can also be written as F is equal to m into g. Now from this we can cancel m and m, and we remain with a is equal to minus gx divided by L. So why a here? Because this equation is nothing but ma is equal to mgx divided by L. M and M will get cancelled, and we remain with a into minus dx divided by L. That's my equation 1. Since g by L is a constant for a given pendulum, length will be constant and acceleration due to gravity will also be a constant. So we can write it as a is directly proportional to x. Hence the motion of the bob is simple pendulum. Now we have the equation a is directly proportional to minus x and a is equal to minus gx divided by L. But we also have the equation for acceleration, that is minus omega square x. Now let us compare this equation with the previous one. So we have a is equal to minus gx divided by L, and here we have a is equal to minus omega square into x. So comparing that, we get omega square will be equal to g divided by L. But what is omega? Omega is equal to root of g divided by L. So omega can be represented in terms of time period, that is 2 pi divided by t, which is equal to root of g by L. We need time period, so t is equal to 2 pi root of L by g is the desired expression for a time period of oscillation of a simple pendulum. So from this expression, we can conclude what are the factors that affects the time period of simple pendulum. Since the expression is t is equal to 2 pi root of L by g, the period t depends on the length of the pendulum, that is L, and it is independent of the mass of the bob, and it is also acceleration due to gravity because g value is constant at that place. So these are the factors that affect the time period of simple pendulum. So next we'll move on to seconds pendulum. What is the meaning of seconds pendulum? A pendulum whose time period is 2 seconds is called as seconds pendulum. We can find the effective length of seconds pendulum. So how to find that? With the help of our time period expression. We have t is equal to 2 pi root of L divided by g. The pendulum whose time period is 2 seconds is simple pendulum. So now let us substitute this to find the length. We need length term, L term. So let us simplify this. To remove the square bracket, we shall square the equations on both the sides. So we get t square is equal to, squaring this will get 4 pi square into L divided by g. So L is equal to t square into g divided by 4 pi square. Now for seconds pendulum, t is equal to 2 seconds. So now substituting the same in this equation, we get 2 square into 9.8 divided by 4 into 3.14 the whole square. Now 2 square is nothing but 4. 4 and 4 will get cancelled. 9.8 divided by 3.14 the whole square, we will get 0.99 meter, which is almost equal to 1 meter. So the length of seconds pendulum is 1 meter, or it can be 100 centimeter. So next let's move on to the types of oscillations. The first one is free oscillation. What do you mean by free oscillation? It is defined as the oscillation of a body when it oscillates with its own frequency. For example, oscillation of bob of simple pendulum, the oscillation of prongs of tuning fork. So when you tap the tuning fork on the rubber band, we can observe the vibrations in it. So that is also an example for the free oscillation. So next one is forced oscillation, which is quite opposite to free oscillation. So when the body is subjected to external periodic force, it oscillates with the external periodic force. Such oscillations are called as forced oscillations, which means that in case of forced oscillations, the oscillation of an object is due to the external force. It is not just as free oscillation. For example, when stem of tuning fork is pressed on a table, the table surface will also, we can feel the vibrations of a table surface. When tuning fork is tapped on a rubber pad and placed on a table, we can just feel the vibrations, which means the tuning fork is now forcing the table to vibrate. So that's an example. And also the other example is the diaphragm of microphone executes forced oscillations when sound waves fall upon it. So the next type of oscillation is damped oscillation, which is nothing but the oscillation whose amplitude decreases with time. So the amplitude of a oscillation decreases with time is called as damped oscillation. Here maximum displacement is nothing but amplitude. So when the amplitude decreases with time, we'll say it as the damped oscillation. For example, oscillation of bob of simple pendulum in air, and also oscillation of prongs of tuning fork in air, because due to the resistance power, because due to air resistance, these will come to rest gradually as time goes on. So the amplitude will decrease. So this is the best example to understand damped oscillation. And the causes of damping oscillations are the viscous force or air drag or friction at the support opposes the oscillations. So the main causes for damping are viscous force, air drag, and the friction at support. Because of this, the amplitude will decrease gradually. So this is the graphical representation of damped oscillations. And we must know about certain terms like natural frequency. What do you mean by natural frequency? It is defined as the frequency of free oscillations of a body. For example, frequency of oscillations of simple pendulum, you know what is frequency? That is number of oscillations that takes place in a second, and frequency of oscillations of prongs of a tuning fork. So this concept of natural frequency is important in understanding resonance. So what is resonance? The phenomenon in which the frequency of forced oscillation equals to the frequency of the vibrations of a body naturally, then the body oscillates with large amplitude, and it is called as resonance. So we will all come across this resonance in our daily life. So we have few examples here. So it is that in sonometer experiment we observe the resonance. The paper rider will be placed on a sonometer wire, and when the tuning fork is tapped on a rubber pad and just placed on a sonometer, because of this vibrations, the natural frequency of the tuning fork will match with the forced frequency just created by the tuning fork, and when these two matches, the amplitude will be more, and this causes that the paper rider placed on a sonometer will fall down. So this happens when the frequency of sonometer wire and the knife edges matches with the frequency of tuning fork. And also the other example to understand resonance is a loud sound is heard due to the resonant oscillations of air column when the excited tuning fork is held at the open end of the tube. So this loud sound is due to the frequency of air column matches with the frequency of tuning fork. When these two frequencies matches, there causes a larger amplitude, and hence because of that reason we will be able to listen to the sound produces in the column. So dear children, in today's session we have learned two important derivations and a few important concepts which are very important examination point of view. So see you all in the next session. Until then, keep learning all of you. Thank you.